Yeah, cool. I can start. Hello everyone. I would like to share my work about like digitalization, both the decarbonization, accelerating the net zero from perspective of carbon capture and utilization. This work is my PhD work under supervision of Professor Alex King and with some collaboration with MITAB22. Let's move to the form section about this research. I will go through the background and the research question, and also what's the methodology, followed by the problem solving. When we talk about net zero, actually it means cutting the annual emissions to the zero by the middle of the century. And International Energy Agency reports like around 3/4 of greenhouse gas emissions come from the energy sector. So that means that net zero can be nearly equivalent to the decarbonization of the global energy system. This can be achieved by the transition from the supply side basically is fossil fuel based power generation to renewables on the supply side and electrification on the demand side. It's actually a long way to go, and in short term, the fossil fuels are still required to maintain the energy supply. And so what we consider is a kind of intermediate solution, which could be applied carbon capture to reduce the greenhouse gas emissions from the fossil-based power generation. So basically, that's what we're talking about, the carbon capture. The full name for the capture system actually is the carbon capture, utilization, and storage. Basically, this technology captures the CO2 emissions from any carbon CO2 sources, and then concentrate the CO2, and then storage the CO2 to the underground. And alternative, the CO2 can be converted to some chemicals or fuels with the assistance of some other kind of inputs like hydrogen. That's a typical chemicals to convert the CO2. And one thing we really need to notice is that energy is actually required for this carbon capture system. And this is normally not mentioned in many research works, or we just say like we use like kind of renewables energy to supply this part of energy, or like use the renewable energy to generate the so-called green hydrogen. So let's kind of introduce our research questions. As we said before, we consider like using fossil fuels to supply the energy system, but that causes a lot of greenhouse gas emission. That's not a good solution. Well, if we consider like fully depend on the renewables, that's it's not available, because the renewables are not sufficient to supply the energy. And if we consider like the CCU system, let's normally say, okay, hydrogen or like renewable electricity are required. So that's however, such a combination actually it's not helpful to identify the bottlenecks for the CCU system. So for example, relevant research or kind of company or startups often claim that cheap renewable hydrogen or renewable electricity is the hotspot for the CCU system. But actually, you can see the renewable electricity or hydrogen actually doesn't belong to this CCU system. So, and also another problem is the whole CCU system has never been fully optimized. So here, our hypothesis is to separate the CCU from the renewables through optimization. We want to check whether the CCU can reduce the CO2 emissions or not. To answer this research question, we propose a hypothetical industry park. In this industry park, we have like 2 power plants, and natural gas is kind of energy energy materials to supply this power plant. And for the flue gas from this power plants can be captured by the 2 carbon capture technology. One is the MEA and other is the PSA to concentrate the CO2 from the flue gas to high concentration of the CO2 to nearly like 90%. And then the captured CO2 can be converted to the fuels product through the Fischer-Tropsch process and methanol synthesis process. Actually, we are facing a kind of a very large energy system in the process level. So we just did a conceptual design for this industry park, or for this industry park, we also call it overall system. This overall system consists of 4 subsystems. The first subsystem is power plant integrated with MEA process for the CO2 capture. The second one is power plant integrated with PSA for the CO2 capture. And then the third one is basically kind of reforming integrated with Fischer-Tropsch for the CO2 conversion. And the first one is reforming with methanol synthesis for the CO2 utilization. And for the first 2 subsystem can produce a low carbon electricity, and also for the CO2 utilization process requires the energy or utility for these 2 subsystems. To achieve the best performance for the overall system, we need to use the optimization here. The optimization objectives can be reduce the CO2 emission as much as possible and maximize the profits for the whole system. To achieve that, we can adjust some operating conditions for the subsystem. For example, in this PSA, what we can do is we can adjust like operating condition like pressure and durations for this process. And also, we also can adjust the distribution of CO2 to the utilization pathways. For example, ZFT is kind of a fraction of CO2 going to the Fischer-Tropsch, and then one subtract ZFT is kind of a fraction of CO2 going to the methanol synthesis pathway. Additionally, we can consider like the heating can be substituted by low carbon electricity. So now, before optimization, we still need to model a subsystem. Each subsystem can be quite complex. The current industrial practice involves the application of tailored simulators for a specific system. For example, we use ICM. It's basically a simulator developed by Carnegie Mellon University to simulate the power plant and MEA process. We use the Daimler to simulate the dynamic system for the pressure simulation absorption. And also for the typical CO2 utilization as a chemical process, we use Aspen Plus to simulate the Fischer-Tropsch and methanol synthesis. Now we have the process model. We still have some challenges. Basically, this subsystem are in different platforms, so it's not very easy to overall simulation and optimization. And another thing is, if we use this rigorous model for optimization, then function evaluation can be quite expensive. So we must tackle these challenges. Let's introduce our methodology. what we do is we consider using we propose the 3 level of optimization framework. In level 1, it's basically I already showed. It's basically we use for each subsystem we use there are tailored simulators for the simulation, and then in level 2 we use the machine learning to represent their subsystems. And then in level 3, we use using optimization to evaluate the system based on this machine learning based methods. So basically, that's for this subsystem we use neural networks or the machine learning models to represent this, so that to achieve one platform for the whole system and also can achieve the cheap evaluation. So with this methodology, we can start problem solving, basically optimization for the whole system. Initially, we do a single objective optimization based on just for the CO2 reduction. We have this process model inputs and also decision variables. We can have the mass energy balances, and with the emission factors that we can evaluate the greenhouse gas emissions as the objective. Then with the optimizers, we can just adjust the value of decision variables. So first of all, we set the objective as a reduction of greenhouse gas emissions. We compare this our CCU system with conventional process. After optimization, we found a CCU actually can reduce the greenhouse gas emissions by 45%. Also, we noticed that in the initial stage of the optimization, basically, we found some negative values for our objective. So the objective is basically we compare this CCU with reference system. Reference system, basically there's no CO2 capture. We found that this value is kind of negative. That means to capture this CO2, actually the capture CO2, they also need some energy input, and this energy input actually cause more emissions. So that's quite bad. Well, in optimal solutions, that's we found to capture this the CO2, actually we use less CO2 emissions. So that's good. And for this, under the optimal conditions, we just gave the overview of optimal conditions. Here we show yeah. Oh, you see something? Okay, so we just continue. So basically, we found two interesting results. One is the CO2 to the utilization pathway. We found most of CO2 just going to the lower bounds. So that means the CO2 going to the methane synthesis. And for the heating substitution, we found most of CO2 is prefers fully substitution by low carbon electricity. And now let's be more practical. We add another objective for economic factors. So we just in objectives we just add another dimension. So then we do a kind of trade-off for the two objectives. Here's the results for the CO2 reduction. That's the x-axis. And y-axis is kind of profits for the system. We show the kind of trade-off for the for these two objectives. So basically we found to reduce a lot of emissions. Actually, you can see the profits actually is negative. That's just as we said before. And also when we just see a very high profits, then we found greenhouse gas reduction is negative. So that means if we pursue two extreme conditions, then we just sacrifice one target significantly. So when we for the decision making for policymakers, we should pursue some operating conditions in the middle. When we see optimal operating conditions, that's basically the decision variables. We found we found the CO2 fraction to the utilization pathways. We found these optimal values can be distributed like from between 0 to 1. So that means some part of CO2 choose the methane synthesis, and some part of CO2 choose the fish chops. And for the heating substitution, we found like not all of this heating prefers the fully substitution by the low carbon electricity, because when you consider the economic factors in the meantime. So basically that's a kind of, we just summarize the difference between the single objective optimization just for the greenhouse gas reduction, and then compare this with the multi-objective optimization. Basically, we found the trade-off between the greenhouse gas and economic factors. We found like for the single objective optimization, we prefer the methanol synthesis rather than fish chops, and the heating favors like full substitution by the low carbon electricity. Well, for the if we consider the economic factors, then they can allow the optimal solutions allows the coexisting of the two utilization pathways, and the heating favors the partial substitution of by the low carbon electricity. And back to our original research question: can optimization and digital help the CCU to survive without renewable input? The answer is yes, but also not yes, because we really need to be careful, because we found like if there's no optimization, just so we give like random operating conditions, the CCU actually the carbon capture can cause more emissions. Well, if giving a optimal solution, optimal operating condition, the CCU actually can decarbonize the power plants. And for more detailed information, you can go for my recent published publication. One is for the methodology for the 3 level of digitalization and optimization, and basically problem solving is basically for the solve this optimize this large system. Is basically another paper is published over here. So finally, I would like to thank my sponsors and my supervisor for the continuous support, and also together with my collaborators. And also thanks for your attention, and I'm open to questions.
Okay, thank you. Any question? Yeah. If no, maybe I have one not question, but comment. Maybe since you have already got the Pareto optimization result, and I think maybe it's better to go ahead to do some kind of policy analysis. For example, like some carbon price or something like this.
I did some carbon price analysis. That's a very good comment. Yeah, so basically so this part front when that part front is basically we don't introduce any carbon price. It's basically it's 0. But when we just increase the carbon price from 0 to 250, basically this value is suggested by the IEA. So actually we found like when in like carbon price, like this side is basically is this left side is basically the greenhouse gas reduction is very low, and actually you find like when we increase the carbon price, the profits is actually going down. But on the right side, it's basically when we reduce a lot of greenhouse gas emissions, when we increase the carbon price, actually the profits can going up. That's because the CCU system, because this CCU system, on the one hand, they just need energy input, and this energy input can be quite expensive when the carbon price is increasing. But on the other hand, this CCU system also can produce some fuels product, and when the carbon price is increased, and this fuel product also can bring the extra economics profits. So basically, that's kind of our initial analysis, but we don't like go very deep because my background is kind of engineering. I didn't go very far for the policy and economic analysis.
I see.
Yeah.
Maybe Dina, please. Dina.
Thank you very much. Many thanks, Jimmy, and thank you. Excellent presentation. Yeah, I'm very interested about this carbon capture and storage. Many large investors, right, we're turning the investments to green and away from fossil fuels. So
yes.
Do you think carbon capture and storage should be counted as green investments or not green? And also like hydrogen, for example, gray hydrogen, which produced using carbon capture and storage. There's also hot discussions. Should it be counted as green? Like I think Japan proposed to count gray hydrogen as green, but not in other countries. So that's I want to know your opinion. Yeah, should we count carbon capture and storage and gray hydrogen as green or not?
I think that's a very good question, and but this question is, I would say, this also area is also controversial. I would say, because it's also depends on like what kind of a source, like what kind of that's what I mentioned, like what's kind of how you operate the carbon capture system, like what kind of energy source for the carbon capture, basically. And also like when you convert the CO2, you probably need like a hydrogen, and what's how you produce the hydrogen. If the hydrogen also produced by the fossil fuels, like steam reforming from the natural gas, actually you cannot say that's green. And so the so-called green technology, I would say like that should be fully from like renewables, like wind or from the solar. But as I said before, actually that's a very ideal solution, but that's not an available solution. So let's be more practical. We really do the optimization based on the existing system, and the existing system actually is largely depends on the fossil fuels. So I would say like your question is really relevant, and also that's what I'm concerned. Like how we assess this system. I mean that's very interesting. That's very interesting point. I would say like just give you one example, like compare like two cases. For example, the cases in India and the cases in I think in Norway. Like for example in India, people also consider like using this CCS for to capture the emissions from the for coal-based power plants. That's very important. Well, for the like in Norway, there's a startup. Actually, that's such a startup actually is from Switzerland, and what they consider is kind of they consider the CO2 capture from air. Basically, it's a kind of direct air capture. But to supply that direct air capture system, they use the energy source from the basically from the thermal energy from the underground. So that's totally renewable. So that's quite different. I think it's kind of two different strategy. So one strategy is like just reduce the emissions from the fossil fuel-based process, and the other strategy is like we have the extra or surplus or like leftover renewable energies. Now we use this leftover renewable energy to try to storage this part of renewable energy for the CO2 capture. I hope my answer is a bit reply your question, or
yeah, thanks very much. Very good.
Yeah.